interesting chapter here. Chapter 15 is what I consider to be the most challenging part of the whole semester. For several reasons, a lot of the concepts might be new to you. Okay, you deal with derivatives in chapter 13, but you already saw this in a single variable case. Okay, we dealt with multivariable integrals in chapter 14, but I also did this in single variable case. In this vector field calculus, this is really the first time we seriously deal with vectors, multidimensional calculus. So to most of you, this is probably the first time you're looking at this. And the other point, which is probably nice about chapter 15, is when we talk about derivative and integrals, they are calculus, and a lot of the questions are coming from physics, chemistry, a lot of other areas, and you can pull them back to those areas. But vector calculus is actually more closely related to physics, okay, much more closely related to physics. Unfortunately, in class, we don't have any time to talk about where these problems are coming from. So I highly recommend you to read the textbook. Okay, in a textbook, they give you a lot of the real-life problems, especially the problem coming from physics, the flux or the flow, where these vector fields are coming from, and especially where this Green's theorem and a lot of the other theorems we're going to talk about are coming from. And they even give you some ideas of how to prove them. If you're interested in proof these theorems, you can definitely go to the textbook and look at them. But in the lectures, we're not going to be spending any time on this because there are just so many materials we have to cover. And I have to give you plenty of examples and practices. Okay. So that's the first thing I want to mention. I highly suggest that any other of you, especially if you are listening to Brian's YouTube video, come here. Okay. So I don't want any one of you to miss lectures in this chapter. So today I want full attention. Not like the other days I don't need your full attention, but today I particularly need your full attention. So we only have one object to discuss, Green's theorem. Okay. So Green's theorem, I want you to be very clear at the get-go what the objects are. We're talking about a closed curve. So this curve is given by a parametric equation. So parametric equation which is given by xt and yt. This is what we have been dealing with for a long time. So we have xt, yt to describe the x component, the y component. And usually we have the initial time and the terminal time. Okay? So this parametric equation will not only give you a curve, but also gives you the orientation of the curve. And also we agree, our default orientation for all the curves is counterclockwise. Okay, so counterclockwise. And in Green's theorem, not only we have this curve, but also we have a closed curve. A closed curve, last lecture, I told you about how do you understand the curve is closed. A closed curve means you begin from a point and then you end at the same point. So essentially you're asking R of A is equal to R of B. Right? So essentially as long as we have the initial point coinciding with the terminal point, then this curve is going to be closed. So this is the geometric object, a closed curve, and then you will enclose a region R. And so this is in R2. So a curve orientated in the counterclockwise direction, and then a region is bounded by this curve. So this is the geometric object. And we have a vector field, which is given by f x1 and g of x1. Okay? So from the get-go, we are dealing with these two objects. We have a vector field in R2, so you can imagine there are a whole bunch of small arrows at each point. Right? So there's a field of arrows on R2, and then you have an object as a region in R2 bounded by a closed curve oriented counterclockwise. Are clear? So this is our object. Throughout the lecture, we are talking about a closed curve and a vector field. And Green's theorem says if I'm taking the line integral on the boundary, okay, which is the closed curve, f dot dr, I'm getting the double integral in the interior of the curl of the vector field. Okay? So two objects are linked by this Green's theorem. Okay? And I call this fundamental theory of calculus about vector fields in R2. Essentially because on one hand, it is a line integral which is on the boundary. And the right-hand side is a double integral in the interior. And this is the general principle of fundamental theory of calculus. In fundamental theory of calculus, you only equate two quantities. One is on the boundary, the other one is in the interior. And this is exactly what it is. So that is essentially why we set up our geometric object of this form, right? You have to have a closed curve in order to have it to be a boundary of some region. All right? If it is not closed, you cannot easily say this is the boundary of any nice region. So we have to have it a boundary. And also there are different notations about each side. In the very beginning, we have this to be the line integral f dot t ds. All right? So in the very beginning, we have this notation for the line integral on the smooth curve. Here t is the tangent vector, right? So t is the tangent vector. And the right hand side is nothing but partial g over partial x minus partial f over partial y. Okay? So these two are talking about the same line integral. These two are talking about the same double integral in the interior. Okay? And in fact, we can rewrite this line integral on the boundary in a slightly different form as well. So I'm going to use these two f and g and also this x and y. Okay? So if I'm using capital F as my vector field with f and g as the two components, f dot dr is essentially just f dx plus g dy. Okay? Here I'm using the fact that dr is just the dx dy with two components. So this is dx dy. Alright? F is f and g. So I do a dot product between these two vectors. I'm going to get f dx plus g dy. That with me? So I have three different notations for the line integral, but they are all coming from the same principle. I'm doing an inner product between the vector field and the tangent vector coming from the smooth curve. Then the right side is a double integral, and this has to be a scalar function. Right? So we can only do a double integral if your function, the intermediate function, is a scalar function. All clear? So this whole thing is going to be our main object today. So the Green theorem equating two integrals. One is in the interior, the other one is on the boundary. And they are pretty understandable. On the boundary, it has to be a dot product. And the interior, it has to be a double integral in a scalar function, right? So think about the double integrals we have been doing before. There's no vectors involved there. So double integral has to be a scalar function, okay? So I want to single out one representation here. So I have a line integral f dx plus g dy is equal to the double integral partial g partial x minus partial f partial y. Okay. So this is one of the representations in the Green theorem. And we actually talk about this Green theorem a lot in a very special case. The special case is when this integrating function, the curl of the vector field, vanishes identically everywhere. All right? So when this guy is equal to 0, I have the condition that partial g over partial x minus partial f partial g is equal to 0. And this is equal to the curl of the vector field. This is exactly the case where the vector field is conservative, am I right? If the vector field is conservative, then the curl of the vector field is equal to 0. Or if you prefer to write in the symmetric differentiation form, if you take the symmetric differentiation, this is equal to 1. They're equal to each other. So a vector field is conservative if and only if the curl of the vector field is equal to 0. All right? If and only if the curl of the vector field is equal to 0. If and only if f is equal to the gradient vector of some scalar function, right? Function phi. Okay. So in order to determine whether a vector field is conservative or not, if you can find its potential function, then immediately you know it is conservative. Or you can check the symmetric differentiation is equal. Right? This is exactly what we did for the last several lectures. Right? Given any vector field, we check whether it is conservative by taking the symmetric differentiation. Okay? And then actually we find this potential function phi. And now there's one different verification. If a vector field is conservative, then taking the line integral of any closed curve is always going to be equal to 0. It's equal to 0 for all closed curve. So 1, 2, 3 different verifications. So if I give you a vector field, if this vector field is conservative, then you take the symmetric differentiation is equal to 0, if and only if the curve is equal to 0, if and only if you can find it's a potential function, and if and only if you take the line integral for any closed curve, it is always equal to 0. So essentially we have 3 different criteria to check whether a vector field is conservative or not. Okay? So vector field is conservative. This is a very, very special case. If you look at these conditions are so nice. All right? Especially the very last one. This one is quite surprising. One thing you have to take away from calculus is you have to be able to appreciate some of the mathematical results, why they are powerful. This is quite powerful because it is true for all closed curves, regardless of where a closed curve is and how the shape is look like. Are you with me? So this is a quite powerful criteria. For any conservative vector field, its line integral along any closed curve is always equal to 0. And these 3 conditions are actually equivalent. You can use each one of them to define what a conservative vector field. Okay, and use the other one as your condition. Okay? In the very first one, it is also called irrotational. It's also called irrotational. So essentially, I give you a lot of concepts, which is really not my favorite part of mathematics. But in any case, at least in calculus sequence, unfortunately, you have to be able to remember a lot of things. And this is a part of that. So a vector field is irrotational if the curl of the function is equal to the curl of the vector field is equal to 0. But that's equivalent of saying the vector field is conservative. Okay? I didn't introduce any new concept. It's just a different conditions for the same conservative vector field. Okay? Questions? Michael, you have a question? No. Okay. So you might wonder why is it called irrotational, right? You might wonder why it is called irrotational. How it is related to the rotation action of a 2-dimensional object, right? So one thing I can quickly explain. Again, if you want to see the whole picture or the whole story, it's much better to go to the textbook and see the explanation over there. Okay? So again, imagine if you have a closed curve, and this closed curve has an orientation, and at every point on the closed curve, you have a small arrow coming out for the vector field. You may have this kind of directions. Okay? All right? And these small arrows are defined by the vector fields. All right? So I have a closed curve. There are 2 independent objects. Are you with me? A closed curve is there. Then I can throw in a field of vectors. Am I confusing you? I have a closed curve, and this is purely a geometric object. It's just a curve, nothing to do with the vector field at all. And then I throw in a field of small vectors. And these small vectors as a field will define a vector at a single point on the smooth curve. All right? So if you can imagine, if you go along this curve, these small vectors are pulling this curve in different directions with different magnitudes. All right? So if you combine all these small forces together, you might have a total action of whether you're pulling this curve counterclockwise or clockwise. Are you with me? So whether you're pulling this in the other direction or the other direction. So there are 2 directions to go, and then you also have a magnitude of how you are pulling this curve in each one of the directions. Are you with me? And irrotational says if this vector field is conservative, then you add all these pulling forces together, they're not doing anything. So this curve is not rotational at all under this vector field. That's why it's called irrotational. Are you with me? So this is sort of like pulling a train, but only this train is actually a curve, which is also closed. If you have a closed curve, imagine you have small forces at each one of the point on the curve. They're pulling in directions and magnitude depending on the vector field. You add this together, you're actually taking the line integral. But if the vector field is conservative, adding them together is always equal to 0, which means you're not pulling this closed curve in any direction. Okay, this is going to be a very stable curve. It's going to be staying at where it is. It's not going to be rotational at all. Okay? Questions? So this is the concept of what this is. And this line integral here is also called a circulation. Again, I have to apologize. I have no option but to introduce so many different English words. But they are definitely, they're just the same thing with different names, which personally I'm not a big fan of that. But unfortunately, if you're doing the homework, they throw in all kinds of these fancy words, whether you're doing the circulation or line integral or whatever. But they're just talking about some the same mathematical object. Okay. Okay. So I want to practice this green theorem on several examples, which I consider will be much more important than a couple of new words. So the first example I want to do is the following. So the vector field is given by minus 4y and 3x. Okay? As I mentioned in the very beginning, we have two objects. One is a closed curve, the other one is a vector field. So these two are actually independent. Okay? I have a vector field. I can have a closed curve, I can have a non-closed curve, I can have a whole bunch of curves. I have a closed curve, and this closed curve can be independent of any vector field. Right? So these two are totally different, which means as long as I have the representation of the vector field, I immediately can check whether it is conservative or not. Am I right? This should be completely independent of this closed curve. Can you check whether this guy is conservative or not? Is it? Is it? No. It is not, right? I have 1, 2, 3 ways to check. One most frequent way is probably to take